In this video, we are going to talk about the hypothesis between two continuous variables, which is the correlation. Now, before we go into the correlation, let's go through this one more time. Okay, so the level of dependent variable, the level of measurement of dependent variable is a continuous, and the level of measurement of the independent variable is also a continuous. Then we're going to use the correlation to test if there is a significant relationship between the dependent variable and independent variable. So the correlations, there are so many different types of correlations, and one of them is the Pearson correlation, which is the one we focus on. It is a bivariate statistical analysis used when the dependent variable and independent variable are both continuous. The question of the correlation analysis asks like when the independent variable increases by 1 unit, what will happen to the dependent variable? Okay, so the assumption behind this correlation, especially the Pearson correlation, is that the relationship between the independent variable and dependent variable is a linear relationship. So the relationship of them can be represented by a line. So what does this mean? So we will see in the next slides. So we have two types of correlation. One is a positive. Of course, the positive basically means 1 unit increases in the independent variable will have an increase in the dependent variable. It doesn't have to be 1 unit increase. As long as it's an increase, then it will be a positive correlation. Okay, the negative correlation is when a 1 unit increase in the dependent variable, a reduction or a decrease will happen in the independent variable. So the highlights here is the more simple way to say it. For the positive correlation, it's as the independent variable increases, the dependent variable also increases. In the negative correlation, as the independent variable increases, the dependent variable decreases. Okay. So the relationship between correlation and it is between the two variables, if they have the correlation and they are supposed to be a linear relationship. So what does that mean? So you can see here is that in the first picture I have x, y, and those are the dots about the results. So this is a really a positive correlation, right? And it's a linear because you can sort of draw a line and to cover all the dots here. Okay, as the x increases, you can see as the x increases, y is also increases. Like when we have the x here, the y is here, right? When we have the x increases, the y also increases. On the right corner, it's a negative correlation. As the x increases, the y decreases. So it's also like a linear regression. You can draw a line sort of to cover all the dots here. And you can see as the x, like here, y is here. When x increases, y actually going down, right? When x increases, y actually going down. So the one here on this one, it's sort of a random. You can't really draw a line like this or this or this or this. It's sort of a random. So this picture suggests there is sort of no correlation, or the x and the y has nothing. They two have no significant relationship, or we say no correlation. Okay. Excuse me. So the linear relationship is affected in a R coefficient. This is one of the unique things in correlation is that we use the R to represent the test statistic in the correlational analysis. Keep this in mind. Okay, so the R coefficient or the R simply we say the R range from -1 to +1. And the population correlation coefficient is rho, which is the Greek letter rho. Okay, so the zero correlation means there is no relationship. The negative correlation means there is a negative correlationship. The positive coefficient means there is a positive correlationship. Okay, you can see this R is basically used in the the sample, and when the population, we use the rho as the correlation. The correlation analysis, we use the t-distribution. Okay, again, t-distribution, it has a good thing is that it can overcome the small sample problems. So whether it is a small sample less than 100 or might be the larger sample over 100, the t-distribution will be a very good one to use. Okay, so most of the time we are going to use the t-distribution to test the significant relationship between two variables in the correlation. So that's it. Okay, because it can use in the small and the large sample size. It's very flexible. Okay, so the method for calculated correlation is to first calculate R, which is a coefficient, and also the test for the significance by comparing the critical and obtained. So compared to the previously ANOVA t-test that only run the critical and obtained, right? And even the chi-square, we have the chi-square critical, chi-square obtained. In the correlation, there is one more thing we needed to calculate is the correlation coefficient, which is the R. And we will use the R to calculate the t obtained. And we will show, I will show you this process in the future example in this PowerPoint. Again, 5 steps. Although we will have to calculate the R first in order to get the t obtained, but in general, the steps are the same. Okay, first step, state the null and alternative hypothesis. Second, identify the distribution. Now in the correlation we just mentioned, we use the t-distribution and compute the degree of freedom. Then we use those information in the step 2 to find the t critical value. And then we use the R, we calculate the R, and also we use the R to calculate the t obtained. Okay, so in the step 4, and the same, make a decision about whether there is a significant relationship between dependent variable or independent variable. It depends on comparing the critical value of t and the critical value, the obtained value of t. Okay, so whether we reject the null hypothesis or accept the hypothesis is really based on the results from step 3 and step 4. So let's take a look at an example. The research question asks whether there is a positive correlation between the extent to which a prisoner's actual inmate population exceeds its rated capacity and the number of major disturbances in the prison. So what does this mean? It's basically like every prison is supposed to have some population limit, right? You can't really put everybody in the prison, or you can't put too many people in the prison. So, but in reality, we put lots of people behind the bars, and lots of prisons are overcrowded. And we want to see if the overcapacity will have some problems related to the major disturbance happening in the prison. Okay, so here is the here is a kind of the example here, and I didn't put anything here, but you can see as here we have different prisons, 1, 2, 3, 4, 5, 6, 7. So we have 7 prisons. Each of the prison has the number of overcapacity and the major disturbance they have. Okay, so like for the prison A here, it put 50 more people in the prison, and it has 3 major disturbance. And for the prison B, it put 70 more, it has like 6 major disturbance. For the prison C, it doesn't have any overcapacity, but it still has 1 major disturbance. So here's the thing. Okay, so in this case, there are 7 prisons. Each of the prison that has a number of overcapacity and a number of major disturbance. Now again, you can see the number of overcapacity here is a continuous variable, right? The major disturbance here is a count. it's also a continuous variable. So to continuous variable, we are going to use the correlation. Okay, and we in this formula we just assume that this overcapacity is the x and the major disturbance is the y here. So let's go through the 5 steps. Step 1 is state the null and alternative hypothesis. The null hypothesis in a correlation suggests that there is no correlation. Okay, very simple. So the rho equals to 0. Rho is a population correlation equals to 0. There is no correlation. Okay. Since the correlation uses the t-distribution and these 3 options of the alternative hypothesis are the same as those in t-test, do you remember that? When we talk about in the t-test, we talk about mu1 equals to mu2, and the alternative hypothesis will be mu1 unequal to mu2, or mu1 is larger than mu2, or mu1 is smaller than mu2, right? Since the correlation uses a t-distribution, we also have those 3 options, and these options, really which options you use is really decided based on the research question, as we mentioned before. So you have 3 ways to do that, just like the what happened in the t-test. The first is that you don't know the direction, but you think there is a significant correlation. So you put the alternative hypothesis as a rho on is not equal to 0. There is a correlation, but you don't know the direction. Second is that you know there is you assume there is a significant correlation and you assume it is a positive, so you put the rho is larger than 0. Okay. So the third one, which is the last choice, is the rho negative is less than 0, which means the rho is a negative number. That means there is a correlation, a significant correlation, and the correlation is negative. So in this research question, whether there is a positive correlation, it's already giving you the information that we are going to use the rho is larger than 0, as suggests that our alternative hypothesis is there is a positive correlation between the overcapacity and the number of major disturbance, right? Easy. Second, we know we want to identify the distribution and the degree of freedom. The distribution in the correlation test is T. We mentioned this before. And the degree of freedom is easy to calculate. It's just the number of the cases minus 2. Now, again, here, I emphasize that there are only 7 prisoners. Okay, 7 prisons, I'm sorry. There are 7 prisons. Each of the prison has overcapacity and major disturbance. Okay, like this one. So what you see is that we have the total cases is 7. The sample size is 7 minus 2, which the degree of freedom is 5. So some people may confuse like we have 14 numbers. Yes, we do have 14 numbers, but we only have 7 cases because each case produces 2 numbers. One is the number of overcapacity. Second, the number of the major disturbance, right? So find the critical value. It's the same idea like what we do in the t-test, okay? So it is for this example, it is one-tailed, right? We say it's just a larger, okay? It is a larger than 0. It's a positive correlation. So it is a one-tailed alpha level, let's say 0.05 degree of freedom based on our calculation is 5. It goes to the positive side, right? I don't have to repeat this one because you all should be very familiar with this one. If the obtained is larger than the T critical, then we are going to reject the null hypothesis. If it's a smaller, like we're here, then we are going to accept the null hypothesis, right? This is a T payable. You are familiar with that. We have the alpha level 0.05, degree of freedom of 5. So make sure that you pick the one tail, okay? 0.05, degree of freedom of 5, which you have the T value or the T critical value as 2.015. And again, since this is a one-tailed and it is a positive correlation, we only pick the positive number. So the T critical value is positive 2.015. Okay, let's mark it here as 2.015. So the any rejection area is on the right side in the positive tab, right? So any numbers the t obtained value will be here like 3, 4, 5 is going to lead us to reject the null hypothesis. Okay, which is going to, we are going to accept the alternative hypothesis. So any number that is less than 2.015, such as 1, 0, even -1, then we are going to accept the null hypothesis. The same logic as we do in the t-test. So as we mentioned in the previous slides, that you have to, when you compute the obtained value, especially the t-value in the correlation test, the very first thing is to calculate the correlation coefficient, which is R. Okay, so this is the formula of the R. And once you calculate the R, you calculate the obtained t-value, which is used to compare to the critical value is using this simple formula. But the formula of calculating the coefficient R is look like a little complicated, right? But if you take a look at everything here, is that it looks complicated, but it's very easy to calculate if you can organize it in a good manner. So which I produced this working sheet, just like other thing, just like the chi-square t-test ANOVA. If you want to make this thing calculate by hand to understand what's inside of it or what's behind it, then you can use this working sheet to do that. Okay, so this is the original number, and I put the original number here like and this is the original number of the disturbance. The xy means the x multiplied by y, x square, and y square, right? So the bottom is the total x, the total value of y, the total value of x multiplied by y, the total value of x square, and total value of the y square. Okay, it's quite simple. You just you can pause a video and use your calculator to just fill the blank. So once we're down, you will see like we have some information. So I'm just going to talk about the first two rows, right? xy means x multiplied by y, 50 multiplied by 3, that's 150. X square, square the x, square the 50. At y square, square the y. Similarly, 70 multiplied by 6 is a 420, and square the 70 and square the 6. Okay, you have the working sheet, so you can organize everything in a good manner. And the sum of the x, you just add all the things together here, and the sum of the y, you add every y value here. The sum of the xy, you add every xy here. X square, sum of the x square, you add everything here. Y square, you add everything here. Okay, now you have almost everything, you have everything we need to fill the, especially what we need is the bottom 5 numbers that we have. Let's put it here. Okay, those are the one you got from the working sheet. This is the formula. Again, carefully replace those letters or symbols in the formula with the numbers. I'm going to replace it for you. Look like this one. Okay, this is the one that you replace all the numbers. And again, like I showed you here, I'm a person that going to calculate like step by step. Okay, I don't like put everything inside of here and click equal and to get me the final numbers. I do this like a step by step to make sure that all the numbers are correct if I'm going to calculate by hand. Okay, so this is the first step. You put everything, put the number here, and this is second step. You do the sum calculation, and it's the third step, and eventually you have the coefficient, the correlation coefficient as 0.81. Now, since you have that, we will have an easy formula. The obtained t-value will be the R multiplied by the total sample size minus 2, which is a degree of freedom, divided by 1 minus R squared. Okay, again, carefully calculate this part and carefully calculate this part, and eventually you will get the t obtained as 3.10. Now we have the R, the coefficient and obtain the value, t obtain the value. Now we can make a conclusion, right? So let's put the t critical here is a positive 2.015. Rejection area is here. Where is a t of 10? Okay, it's greater than the t critical. So what is our conclusion? Simple. Since we are going to reject the null hypothesis and accept the alternative hypothesis. So what is the alternative hypothesis? There is a positive correlation between blah 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 blah. This is the between the two variables, dependent variable and the independent variable, right? And then you can put one more sentence to explain what is this positive correlation mean. So as the overcrowding increases, so does the number of disturbance is, right? So this is how you solve the correlation. Okay, it's very simple. Let's take a look at the second example. The second example asks a research question is that true that prisons with higher staff to inmate ratio should have fewer disturbance? Okay, so again, here we have how many cases? You can count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have like 10 prisons. Okay, each of the prison provide two numbers. One is the staff per 100 inmates. For the prison 1, the staff per 100 inmates is 4. For the prison 3, the staff per 100 inmates is 12. Okay. The second number the prison provides is a major disturbance. For the first prison, there is no major disturbance. For the second one, there is no major disturbance. For the third one, there is one major disturbance, etc. So you can see we also have the independent variable as the x here, which is the number continuous variable. We have the y here, which is also like a counts of the major disturbance, which is continuous variable. So the correct way that we're going to test if there is a significant relationship between x and y is going to use the correlation. Again, we use the 5 steps. Okay, so the step 1, rho equals to 0. It's not going to change. Okay, the null hypothesis is always the population correlation is 0, so there is no correlation. What is the alternative hypothesis? Because the research question is that the prisons with higher staff have fewer, so as one increases and one decreases, so this is a negative correlation. So the alternative hypothesis will be there is a negative correlation between the two variables. Therefore, the rho, the population correlation, is less than 0. So the second step, identify the distribution, compute the degree of freedom. The distribution, again, we talk about this is using the t distribution, right? The degree of freedom, again, we talk about it's not all the numbers of numbers minus 2. It's the case, the number of the cases minus 2. So we have 10 prisons. So the 10 minus 2, that is 8. Okay. Step 3, find the critical value. At this time, we are using one tail. We already mentioned that, and it's supposed to be in the negative side, right? At this time, we use alpha level 0.1 to see what's going on, and degree of freedom of 8. Okay, it's on the left side, so whatever is less than this t critical, it must be a negative number. Then we are going to reject the null hypothesis. If it's larger than the t critical, whether it is a negative number here or a positive number here, we are going to accept the null hypothesis. Quite simple. So again, here is the t table. You're looking at alpha level 0.1 and you're looking at a one tail. Don't make this wrong. Okay, it's a one tail, alpha level 0.1, degree of freedom of 8. What do you have? 2.896. That is the absolute value of the t critical. And think about that, we use a one tail and we are looking at a negative correlation, which is in the graph, it's on the left side, it's a negative side, right? So this t critical indeed is negative 2.896. Okay, the number we find from the t table is always be the positive. You have to make your own judgment whether you use a positive number here, you use a negative number here, or you use both positive and negative numbers. In this case, we are looking at the left side, which is the negative side, so the t critical will be a negative 2.896. So let's map it. Here we put the t critical as a negative 2.896. So if we have like a negative 3 or negative 7, then we are going to reject the null hypothesis, right? If our t obtained value is like a negative 1 or even positive 1 or maybe positive 2, then we cannot reject the null hypothesis, so we have to accept the null hypothesis. The same logic. Compute the obtained value. There is no difference between this one and the previous example. You use a working sheet. It's very simple working sheet. I'm not going to repeat that, but again, you can pause the video and try to complete this working sheet by yourself. Then you can make a comparison between the one you compute and the one I compute. Okay, again, the most important thing is something in the bottom right. These 5 numbers are the one we are going to use in the formula, so you can put it down here. Okay, the sum of the x, the sum of the y, the sum of the x multiplied by y, the sum of the x squared, the sum of the y squared, and this is the R formula. One more time, carefully replace all the letters, symbols with numbers, and carefully use your calculator to calculate this R. So eventually the R, the coefficient we get is negative 0.14. Okay, what's the next step? Okay, so we use this R to calculate the t obtained, right? Again, carefully replace all the letters in this formula, okay, with those numbers, and use your calculator to calculate that the t obtained we finally get is negative 0.40. Okay, so we can make a conclusion. Where is a t critical? It's negative 2.896. Okay, so where is our t obtained? Negative 0.40, which is in this area. That is not in the rejection area, so we have to what? Accept the null hypothesis. Okay, so make a decision become very easy. We have to accept the null hypothesis. There is nothing to do with the alternative hypothesis. Okay, the null hypothesis is rho equals to 1. The population correlation coefficient equals to 1. So it suggests there is no correlation between staff to inmate ratios and disturbance. So basically means those two variables are not really statistically correlated to each other. Okay, so this is a second example. Now, a further examination in the correlation, we will doing something when the null hypothesis is rejected. We will try to explain the R a little bit more. Okay, so this is similar to like ANOVA, right? When the null hypothesis in ANOVA got rejected, you will have the post hoc test to see which group is significantly from which other groups. So the similar here in the correlation is that when the null hypothesis is rejected, we will sort of explain the R and the R square and what does that mean to tell us. Okay, so when the null hypothesis is rejected, so basically means we accept the alternative hypothesis. So there is a correlation between the two variables, and we will interpret those correlation coefficient. The very first one is to interpret the R by itself to see how strong the correlation is between the two variables. I give you some a general guidelines. Maybe different discipline in social science have different way or different guidelines or criteria about this one, but typically this is what I usually use. Okay, so the correlation, the weak correlation, the R lines between the negative 29 to positive 29, and in the negative side, so we can move this one into cut it into half. Okay, so for the negative side, so for the negative correlation, right, so the moderate relationship will be the R is between negative 0.49 and the negative 0.30. For the strong correlation is negative 0.69 and between and the negative 0.50. That is a very strong correlation. That is strong correlation. And we have a very strong or super strong correlation is that when the R, the coefficient is less than negative 0.70. Okay, but again, you know that the R must be what? R must be from positive 1 to negative 1, right? So here you can put it here is like it definitely not going to be smaller than negative 1. If you find a coefficient is less than negative 1, what does it mean? There is a mistake in your calculation. You have to calculate again, okay? So on the other side, we can take a look at the positive side, okay? If it's a positive correlation and the coefficient R is between positive 30 to positive 49. It's a moderate correlation. Between the 0.50 to 0.69, it's a strong correlation. And if its R is larger than 0.70 in a positive side, then it is a very strong correlation. Now, again, the R is larger than 0.70, right? But still, it has to be less than 1. Okay, so what if you get R that is like a 2 or 1.5? That means there is a mistake or in the calculation. You have to calculate this again. Okay, so now you can use this one, the criteria, to make a judgment about if the non hypothesis is rejected, that means there is a significant correlation, how strong the correlation is. Okay, so in the example 1, we test whether there is a positive correlation between the overcapacity and the major disturbance, right? And we have the alternative hypothesis. We have reject the non-hypothesis and accept the alternative hypothesis, right? So the previous sentence is there is a positive correlation, or there is a significant positive correlation between the two variables. As overcrowding increases, so does the number of disturbance. And now you can make more and more sentence. If you remember that we have the R equals to 0.81, this positive correlation is very strong. Or you can say the independent variable and the dependent variable has a very strong positive correlation because of the R is 0.81. Okay. We also want to explain a little bit with the coefficient of determination, which we calculated by R square. R square is easy. It's just you what? Square the R, right? Square the R, you get R square. So the R square is a proportion that can be converted to a percent, interpret as, this is very important, a percent of the variance in the dependent variable that is that can be explained by the independent variables. Okay, that means like I have these independent variables, and when this independent variable changes, the dependent variable will change. But as you know, in social science, there is almost no one-on-one relationship. So there is a dependent variable, but there are so many independent variables that can have the impact on this dependent variable as well. But in the correlation, we can only examine one variables. So in the case example 1 is that we only looking at the overcrowding and the number of disturbance, but the number of disturbance may be impacted by other factors such as how old is the prison, right? The facility in the prison, or like who are the prisoners? Are they like violent offenders, or are they just thieves? Okay, these are all the factors that impact the number of disturbance. But we don't look at that. We only look at one-on-one situation. which is overcrowding and the number of disturbance. So again, because of that, we can say that this variable, this independent variable, can 100% explain what's happening in the dependent variable. We can only explain that this independent variable has a significant impact on the dependent variable. And from this R square, we sort of can know that what kind of how much the independent variable has an impact on the dependent variable. Okay, so this is a very important thing. So in the example one, we can further finish our conclusion. Okay, so the previous one, there is a positive correlation between the two variables, right? As the overcrowding increases, so does the number of disturbance, and also interpret the R. Since the R equals to 0.80, this positive correlation is very strong. Okay, now we add another sentence that involved with the R square. So since the R square is 0.66, where does this 0.66 mean coming from? It's the square of 0.81. Okay, it's the R square, so square of 0.81. You got this 0.66. Okay, that's a proportion, right? Change it to the percentage. So since R square equals to 0.66, 66% of the variance in the dependent variable disturbance or number of disturbance can be explained by the independent variables overcrowding. Okay, that's a completely conclusion in the correlation if you have the null hypothesis is rejected. Okay, let me repeat this one. If you reject the null hypothesis in the correlation, which means you accept the alternative hypothesis, this conclusion here is a complete version of the thing you need to explain. Okay, you need to explain the t-value, so it's a significant correlation between the two variables. You needed to explain the r value, the coefficient r. What does the r mean? Okay, it means how strong the relationship is. And also you need to explain what does the r square mean. It means what kind of percent of the variance in the dependent variable can be explained by the independent variables. Okay, so now people ask, okay, there are 66% of the variance in the disturbance can be explained by the overcrowding. So where are the another 34%? Like I said, another 34% of the variance in the dependent variable can be explained by maybe the age of the prisoners, the facility in the prisoners, the crime committed by the prisoners. Are they violent people? Are they not violent people, right? Those are the other factors. But here in this PowerPoint, especially when we're doing the chi-square, when we're doing t-test, when we're doing ANOVA, and together we're doing the correlation, what we're doing is a bivariant test, which basically means we have one dependent variable and one independent variable, or let's say we have only two variables, the relationship between the two variables. Okay. So at last, I want to emphasize this one more time. We emphasize this one in the chi-square test and as well as in the t-test, right? So the relationship, the significant relationship does not mean a cause and effect, does not indicate any causality. So the same applies to the correlation. Correlation does not say which one causes which one. Okay, so although here we use the X to represent overcrowding, we use a Y to represent disturbances, but this is only for calculating the correlation. We can only say that the overcrowding is significantly related to the disturbance. Okay, we cannot say that the overcrowding leads to disturbance. Okay, so this is a big difference between a simple correlation and a causality or the causal effect. So if you took the methods class or you know a little bit about the research method in the social science, that the fact that two variables are statistically significantly related does not mean one truly causes another. And the research methods also tells us that if you want to establish this causality, the cause and effect between the two variables, you need to meet at least all of them. The three things: empirical association, appropriate time order, and not related to a third variable. These three are the necessary factors used to establish the causality or cause and effect. Okay, and also if you want a further one, you need to have the cause and effect explained in the context, and we explain its mechanism. But this is an important one, but does not um, indicate that cause and effect. The first three, these three are the factors must exist when we say there is a causality. Okay, so that's it for the correlation.